We're talking about limits of functions today. I'm going to begin by using their example 1, and then I'll go back to the definition and try to work through that definition. They want me to compare two things, basically what they're doing on example 1. They want me to look at f of 1. So this is, I need the function value when x is 1. So here's my graph that I'm to look at. When x is 1, the function value is 2. The limit is tell me what is going on around that point, and not necessarily what it happens to identically equal. So let's look at what's going around. What are the points that are in the neighborhood of that x equal 1? Where are they going? And in this case, everything is going to 2, both the points in the neighborhood and the function value itself. They're all going to 2. So that's handy when the function value equals the limit itself. That's a nice one. Next, we're going to look at the b part. And on the b part, I'm to find f of 2. So I need the function value when x is 2. When x is 2, the function value itself is way up here, and it equals 5. The limit as x approaches 2 of f of x, I need to know what are the points doing around, not necessarily what the function value itself is, because I don't really care about that. I know about the points around it. Where are they going? And they are going to this value of 3. So the interesting case, the function value and the limit don't necessarily have to equal. We'll look at another one, f of 3. F of 3 is actually undefined. But what is the limit doing? Because the limit doesn't care about the function value itself. The limit is looking at those points around where x is 3. Look at those points around where x is 3, and are they going to a central location? In this case they are. They're going to that value of 4. So 3 unique cases. One where the function value equals the limit. Here we show that the limit doesn't have to equal the function value. And in the third case, the function value itself doesn't even have to exist in order for there to be a limit. Cool. In this next case, we're looking at a table instead of a graph. And in this table, they let me look at numerically what is going on in that neighborhood. So as I get closer and closer to this 1, what are points on either side of this 1 doing? And it looks like to me they are heading to the value of 0.05. I see that I can't physically plug in a 1. I can't plug in a 1 in that case, because if I did, I would have a 0 in the denominator. But I can still look at it graphically, or I could look at it numerically and get that value of the limit. But don't be lulled into thinking this will always get you the limit. We'll look at a case in just a few minutes where we are given a teaser and it doesn't quite equal what we think it might. I graphed for you using my TI-84 calculator the function that they want us to look at. We're looking at this function x cubed minus 8 over the quantity 4 times x minus 2. I'm looking at this function. That is what I graphed in my calculator, and this is my picture. Notice this unusual looking hole. This hole happens because numerically and analytically I cannot physically put a 2 into that function. F of 2 does not exist. So does not exist. We'll call that D N E, because that would make that denominator 0. However, I will have some limits that are occurring here. When I look at these two, this limit x approaches 2, and this little plus thing means from the right. As I approach 2 from the right, and physically what I do is I take my right hand, and I wish you would do this with me. Take your right hand, and this is going to make a difference not on this problem, but it will on others. So take your right hand, and from the right, go to that point where x is 2. And I try to figure out, where is this going? And looks like to me, if my y's are scaled at on the ones, which they are, appears to me that this function is going to 1, 2, 3. If I look at the limit as x approaches 2, whoops, try that again, 2 from the left, so that would look like 2 from the left of f of x. That means I take my left hand and I go towards where x is 2, and I say, what is that y value there? And on this one, it is also 3. So this minus means from the left. I would take my left hand and just get in the practice of taking your left hand to find out what this might equal. Let's look at what the textbook in its solution gave you. They gave you a computer generated graph, and on your older TI-84 calculators, this is exactly what you will see. You will not see that hole. It will look as solid as can be. I wanted you to see it with the TI-84 because they have upgraded a little bit to show you that hole, but you really have to look close to see that little hole. The accurate plot is one where you physically draw that hole, so technically the TI-84 should have done something that looked a little bit more like this to show accurately that there is a hole there. Going up to the definition, I have a right hand limit, and this is saying look at those points that are approaching that x, but only look at the points from the right. The left hand limit tells you to do the same thing except for from the left. Then our next theorem will say that if the left hand limit equals the right hand limit, then the limit exists. Notice that the left hand limit and the right hand limit are equal. Therefore, I can say that this limit exists. So they also want me to find the limit as x approaches 2 of f of x. This also equals 3, and it equals 3 because of the theorem that will be proved later on in the course. The right hand limit equals the left hand limit. If this is the case, if this is our case, then the limit exists. Naturally, we want to look at some left and right hand limits, some where maybe the left hand limit doesn't equal the right hand limit. So here we go. You will see several of these in your homework. This says look at your g of x and what are those values approaching from the left. So as x gets closer and closer to 2, the y values that they're approaching would be that value of 4. As x approaches that 2 from the right, those y values, well, they're holding steady at 1. The limit itself does not exist because the left-hand limit does not equal the right-hand limit. So I will write because limit x goes to 2 from the left, of g of x, does not equal the limit as x goes to 2 from the right of g of x. We looked at a limit from a table, and if I were to ask you to just look at the table and not look at the graph quite yet, but if I were to ask you to look at the table, as I'm approaching, I'm wanting to know what happens as x approaches 0. As I get closer and closer to 0, this table looks like it's approaching a -1. However, when I go even further, I see that, well, that's not a 1, that's a positive -1. It's a positive 1 here. And then it swaps back over to the negative. The reason for that is because this cosine of 1 over x is oscillating so rapidly, it's bouncing, you'll notice from the graph, bouncing back and forth from 1 to -1. And the closer you get to 0, the faster it's bouncing back and forth between 1 and -1, not approaching a singular value. So this limit would not exist. But it would not be obvious from just the table. Unless maybe if you just only plotted 3 values, you would think that it did exist, but once you plotted that 4th, you go, something funny is going on here. So sometimes you need to extend your tables just a little bit. Pictures do you a lot of good in looking at limits. All right, and I think that's it. If you have any questions, be sure to join me at the Collaborate or send me an email or put a question up in the discussion board. I'll be checking that every single day.